Have you ever seen anything like that before? Marvellous, isn't it? It's called a microcraft, a one-man air transporter. You know, it was only 80 years ago that an aeroplane driven by an engine actually flew for the first time. 80 years. That's during the lifetime of some of your granddads. Those early attempts to fly really caught people's imagination. Soon it was thought everyone would be flying. We would all have a flying machine parked in the back garden next to the greenhouse. Well, 80 years have gone by, and this is the nearest we've come to reaching that. But the interesting thing is that those early flying machines looked a bit like these modern microcraft. It took a lot of time and effort to achieve that first aeroplane flight. The problem wasn't actually how to get off the ground in the first place. There were engines around that could supply the power all right. What was hard, though, was finding materials strong enough to build the aircraft. And there was another serious difficulty: how to actually control the plane once it was off the ground. How to make it climb or dive, to turn left or right, or to roll one way or the other without dropping straight out of the sky. Have a look what I mean. The oldest British aeroplane still flying is the Blackburn. It flew for the first time in 1912. It's quite a job getting in, isn't it?
It certainly is. They didn't design these as comfortable limousines.
Now, this is the main control, is it?
That is right. It's like the wheel of a car, and it turns not very far, but like the wheel of a car. And when you turn it to the left, for example, you'll see the wing warps. That side goes up and the other side goes down, and that causes the aircraft to bank.
Yes, I see. It twists the wing one way and at the same time twists the other wing the other way.
That is right.
And what does that do?
Well, that causes the aircraft to bank for turning.
So that's how you turn it to the left and the right?
That's right.
Right. And how do you make the plane climb or dive?
Well, we use the same control, but in a different direction. We move it backwards or forwards. If we move it stick back, the elevator comes up, and that causes the nose to rise.
Yes.
If we move it forward, the elevator goes down, and that causes the nose to go down.
David explained that the controls of an aircraft cause the wings and the tail to disturb the air that flows past the plane in flight. If one wing is twisted upwards and the other wing is twisted downwards, then the plane will roll. If the rudder is moved at the same time, then the plane turns. Twisting the elevators on the tail down causes the wind to push the tail up, and the plane dives. By using the three controls on the wing, the tail, and the rudder, an aeroplane can be moved anywhere in the sky.
This is the Tiger Moth. This particular one was built 41 years ago, although the design goes back another 10 years earlier than that.
So the first one was made in 1931?
That is right, yes.
Now at the back there I can see the rudder and the elevators.
Yes.
Where are these ailerons you were telling me about?
Ah, they're here on the wing, hinged, you will see. But it's better if I show you by actually moving the control column. You'll be able to see that they go up and down. One goes up when the other goes down, and they provide a much more positive form of control than the wing warping on the older Blackburn.
Right. Well, you've got your flying hat in your hand and you're wearing your flying suit. Why don't you go and put her through her paces?
We'll see what we can do for you.
All right. See you later.
Right.
David Ogilvy, the pilot and my guide at the Shuttleworth Aeroplane Museum, then showed me how the Tiger Moth could be made to move in the sky. First, some banks and turns. They use the ailerons and rudders together. Then a dive, controlling the aeroplane with the elevators at the back. Finally, the Tiger Moth landed, with David using all three controls to bring the aeroplane to a smooth touchdown. By making adjustments on the wings and tail of a paper glider, it's possible to make them bank and turn, like a real aeroplane. The Wright brothers eventually solved the problems of controlling an aeroplane in flight using the systems we've seen. And those solutions are basically the ones that are still used on modern aircraft, from a two-seater to the mighty Concorde. But anything that flies presents problems of control. Take rockets, for instance. Part of the problem with rockets was to get them to go where you wanted them to. A brilliant German rocket scientist named Werner von Braun eventually solved that problem. He arranged that the rocket motors should do two things. They should push the rocket into the air, and also the jets themselves should keep the rocket on course, that they should steer it. Von Braun's aim wasn't to put a man on the moon. That was much later. He put explosives inside and aimed his rockets at London, because the first rockets to fly under control and accurately were V-2 bombs that fell on Britain during the Second World War. And that's something else your grandmas and granddads will perhaps be able to tell you about.
Turn it round carefully. Keep your fingers well away. Steady. Now, with the knife.
These young scientists are building rockets with materials collected from the kitchen. They know already that the rocket will fly better with sand to weight the nose cone. Their next problem was to make the rocket travel as far forwards as possible.
Now we can fit it onto the stand. We can put the bag into the back of the rocket to the same position as we had it last time. Just like that.
It doesn't matter, it pushes it air through, pushes it into the...
The same rocket seemed to travel different distances when fired at different angles.
Exactly.
Just like that. Right.
Some angles of launch were better than others. What else do you think would affect the distance the rocket will travel?